Hello, everyone, and thank you for joining us today. Welcome to Megger's special webinar series. Today's topic is electrical insulation testing of high-voltage gas-insulated switchgear. My name is Michael Fleischer, and I'm the digital marketing specialist for Megger. I'll be acting as your moderator for today's presentation and supporting you on any technical issues or questions for our presenter. On the right side of your screen, you will see a control panel that looks similar to this one. You can submit questions at any time during the presentation by typing in the box highlighted in red, and I will read the questions out during the Q&A segment at the end of the webinar. Additionally, a certificate of attendance, copy of the presentation, and a link to the recording of this webinar will be sent to all attendees in 2 business days. Our presenters today are Volney Naranjo, Senior Applications Engineer, Daniel Carreño, Applications Engineer, and Charles Nybeck, Applications Engineer. All right, let's go ahead and get started. Thank you for joining us today, Volney.
Thank you, Michael, and welcome to everybody to this webinar. Here I'm showing the agenda we have for today. We usually do webinars of 1 hour duration. Today, because it's a more comprehensive topic, we are going to be presenting for approximately 1 hour and 20 minutes. I think it's fair to announce these. You may have plans, so we're going to be covering a little bit of introduction to GIS testing. Then we're going to move on directly into some of the tests that we're going to be talking about or that we are mentioning in this presentation. So we're going to talk about contact resistance, circuit breaker timing. We're going to talk about the instrument transformer testing, and then the last portion of the presentation is GIS insulation testing. I'm going to be presenting up to the dual ground contact resistance. Daniel is going to do the circuit breaker timing and the instrument transformers, and the last section is going to be given by Charles Nybeck. So getting into the first part, the introduction. So GIS, it's basically a gas insulated switchgear, or some people call them substation. The S instead of the switchgear is for substation. In essence, it's a substation or a switchgear that allows you for installation in reduced space, and it has a compact design. Everything is embedded, or all the conductors, the primary conductors, are insulated in SF6 gas. And due to some environmental concerns, now other gases are being developed by manufacturers. So they usually look blue as indication that they are kind of a not so harmful gas for the environment. You can see here in the slide that they're very similar, the slide and the diagram. You have the voltage transformer at the top of the GIS of the arrangement. Then you have a disconnect switch that some of them, they are fast acting switches. Then you have and this is the connection to the bus bar. Then you have another disconnect switch. You have the CT section, you have the circuit breaker, you have CTs on the other side, and then you have a disconnect switch. The output of the cables is this one here, which is the cable sealing enclosure, and you can see that in the picture where the cables go. And up here you can see where the input or the side of the transformer is. So everything is closed, and it's a very compact design, and you can see them in 3-phase or single-phase arrangements, like the enclosure for the SF6 gas. You could have the 3 phases in one single enclosure, or you could have separate enclosure for each phase. So there's a lot to talk about GIS, but we are focusing here only in the testing. So when these switch gears will need testing? Well, there's, like in any electrical equipment, the different stages of the life will need testing. Of course, at factory quality control, factory acceptance test, you would have testing on each of the elements, individual components, and once it is assembled, they will also do all type of checks and tests. As a customer, customers will like to see factory acceptance tests, so that is also common to see that type of testing. During commissioning, of course, you want to do acceptance, site acceptance test, and you want to do startup and all the activities related to commissioning. So though that's another instance where you would have this type of test. And maintenance, well, one of the advantages and one of the characteristics of the GIS is that they have very reduced maintenance. Actually, they are announced or marketed as maintenance free. Of course, we know in the electrical industry, maintenance free means reduced testing and very, very limited activities. So yes, it's not common to test them while they are in maintenance, but there are going to be instances that you need to test. So, and the other kind of a characteristic with the GIS is that they will remain under warranty service for a long period of time. So many times the user or the owner of the equipment doesn't need to worry about the testing, but it is taken care by the manufacturer or the contractor, and then of course they need to do the testing, and they're going to encounter situations where it needs to be tested. Another instance where you would like to do testing is for troubleshooting if a problem happens, or for warranty claims, or after warranty maintenance, after warranty expires. So definitely there's a lot of instances in which it can be tested, and well, not so common or often, but it needs to be done. What needs to be tested? As in any electrical equipment, all of the aspects that we know for other tests kind of apply to these. So contact resistance, you would like to have contact resistance measurements, and especially in these elements that are interconnected. Each of those sections that I showed before, they have like an interface, an interconnection between the different modules, and of course, there's a contact resistance there. So the overall resistance, contact resistance measurement is very important, and is something that you may want to verify. And actually, one of the standards, it's one of the few things that are mentioned in the IEEE standard is about the contact resistance measurement, and manufacturers usually provide the overall contact resistance or low resistance measurement through the entire section. Circuit breaker. Circuit breakers are exactly the same thing as the dead tank circuit breakers. So they have the same type of contacts, they have the same type of main and arcing contacts, they have the same type of operation of a dead tank circuit breaker. And the contacts will deteriorate. You also want to check the phase sync, or the difference between the fastest and the slowest phase. The breakers also have a mechanism, so you also want to probably measure travel. And there's coils and for the operation of the breakers, so you also want to verify those, and those will all very likely fail sometime. So you want to have some measurements on these, and want to do some maintenance testing. Arcing contact, motor current, all of that. Switches, as you saw on the previous slide, there's several switches in the section, and they are motorized switches, and some of them are fast acting switches. So you can measure the motor current, you can measure the travel of the maneuver shaft, and you may want to or you may need to do some troubleshooting on these elements. So those are other things that you can test. Instrument transformers, CTs, PTs, they are the same type of CTs or PTs as any other installation with a different external look, but they are going to have the same parameters as any other CT or PT. And then the insulation. This is a critical part. Insulation is mainly, or it's basically SF6 with some supports inside to kind of hold the conductors. But so most of the insulation is related to the SF6 condition. We do not have anything for that, so we are not talking about SF6 condition. But we do have partial discharge, and partial discharge is something very, very important in the analysis of the GIS or the testing of GIS, and it's probably the most frequent thing that you do, other than the other tests that I've mentioned. So And that's what we are going to several of those things is that we're going to be talking about in this presentation. Then testing challenges. Definitely, there are a lot of challenges. First of all, every time you think on testing a GIS, you need to think about the configuration, because depending on the configuration, you're going to have different situations, different conditions, different challenges. So you need to understand and know the configuration of the GIS. In general terms, this is a constant. There's no access to the primary terminals, and we're going to see a slide that depicts that better. So there's no easy access, or there's no access to the primary terminals and that is from the beginning, from the transformer to the end of the circuit. So there's no way to go and test as easy as when you go and test any other element. Even the transformer, if you want to test the transformer that is associated to this substation, you're going to have issues to test that because you don't have access to the primary terminals. The only access is to grounding links. So those switches that I showed before, in some of them you would have access. The primary terminals are brought out and they are grounded there. That's where those grounding switches actually ground the conductor. So that is the only access, and then we are going to look into that a little bit in detail. Whenever you manage to get access to the primary terminals through these grounding terminals or grounding links, then you may have parallel grounding paths when you are trying to use dual grounding techniques, which is something that we are going to be showing here today as well. And if you isolate and you remove the grounding links, then you're always going to have capacitive coupling there because everything is so close. Everything, the capacitance levels are important enough that they will generate a lot of high voltages induced on whatever section you have ungrounded. So it's very important safety-wise to mind about the capacitive coupling. Then there's a lot of interlocks, and sometimes to be able to test, you need to defeat these interlocks. And the moment that you talk about defeating an interlock, you are compromising safety. So again, you need to be very knowledgeable about the GIS, you're very knowledgeable about what you're doing. If you are testing with the rest of the GIS energized, that is even more complicated, and you can even trip some protections, and that's the next one. So you need to be mindful about that protection scheme. So just to illustrate a little bit more the things that we mentioned before, some of the things, no access to primary terminals. So this is the top of a transformer that is connected to the end of the, or one of the sides of the GIS. So you can see the primary terminals here. There's no way to access the terminals there. You would have to open the enclosure, and of course the SF6 is it's there, so you cannot do that. So at the other side of the wall, you have the same exact GIS that I was showing before, and then you have, this is double bus bar, so you have the bus bar connection here. You go across the other side of the breaker, and then everything comes down to the load. And on the other side of the load, it's going to be a separate building, usually 100 meters away, or some good distance between the GIS building and the switchgear distribution switchgear building. So no way to access primary terminals. What is the access through the grounding links? So in this diagram that we have here, we are showing a GIS, the single line diagram of a GIS that has double bus bar. You have a grounding switch here, you have with a disconnector from the bus. You have another disconnector, this one doesn't have a ground. Then you have the circuit breaker, CT, another grounding switch, PT, surge arrestor that is optional, and then one more grounding switch. So you can see here, there's a little bar here that is representing this access to ground here. So the terminals are being brought outside of the GIS to this bar here. And if we go looking kind of a cross section of these, we can see the bar a little bit better here. And if we take a closer look, we have more detail there. So, and the same happens here on these other switch, disconnect switch, you have the same thing. The only thing is that we are just seeing the side of it. And this is how it looks in some GISs. So this bar here would be exactly something like this here, and then it's connected to ground here. So you see A, B, and C phases connected to ground. You have here in this other picture, you have phase, I don't know, phase A, B, and C here, and this is grounding point. And for this one, this is another way how these links to ground will be done. This is an insulator here between the two sections, and then another example is like this one, that again you have an insulating section here, and you have the grounding link here. So one side is going to be the terminal side, and the other one is going to be ground. And to get access to that, well, what you need to do is to remove that bus bar or whatever connection is getting connecting that primary conductor outside to ground. And when you do that, this is how it looks. So the very first picture, or that, sorry, one of the pictures that I showed before, everything was connected here like diagonally. Now all the links are open. They were left there for purposes of testing. In this one, you can see the link is removed, and you can see that this is a three-phase style GIS. So you have one phase here, second phase here, even a little bit higher in the back, you have the third phase. And another style is this one here. You can, where's my pointer? You can see here, this is the grounding switch, and then this is where the link was removed. This was a link here. So, and when you do that, basically you get this condition that one side of the GIS is grounded and the rest is kind of floating. So any potential, sorry, any induced potential is going to be present here, and that's I think what we are going to be talking about right now, the grounding links and what kind of challenges it poses. So you need to remove these grounding links. Sometimes it's necessary for some of the tests. And when it is not possible, when it is possible, it's not a safe practice. If other circuits in the same GIS are energized, because now you have capacitively coupled currents that are going to induce high values and in between the live and the isolated part. So it's not a safe practice. And here's a little bit of more illustration about it. So in this case, we have this bay here grounded, and if we have, so because it is grounded, it's kind of a safe area. It's no problem. You can easily work there. Even though you still have the capacitive coupling from the other two buses. So if the the buses are energized, they are going to be showing, they are going to be inducing there, but everything's grounded, you don't have any problem. If you remove the grounds, now it's not anymore a grounded, sorry, a safe area. So that's what happens. So this removing the links may not be possible in some cases because the operations conditions or safety conditions or restrictions. So you have to look for alternative testing techniques for some of the elements that you want to test. Some manufacturers are already offering online monitoring, so they will have, for example, online monitoring for the breaker test, for testing the breaker. So it will measure the timing and the travel of the breaker every time that you operate the breaker. This is an accessory, might be expensive, and you may not have these in your substation. So you need to look for other techniques. One common technique is the dual ground technique, and that's one of the things we are going to be talking also here. A little bit of a summary to finalize this section. So here we have some techniques that are available to test different elements. So we have the different elements here: CT, PT, circuit breaker, timing and travel, the circuit breaker coil and motor currents, the contact of the breakers or the switches, and the insulation. And then we have here conventional technique, the typical ones that we know, then the dual ground, first strip, which is a technique for breakers, and other techniques like the voltage detection system that, by the way, it's for medium voltage GISs. Here we are talking about high voltage GIS, but I wanted to mention it because, well, it's another easy way to test GISs, medium voltage GISs, through the voltage detection system. And dynamic resistance measurement, offline and online monitoring or testing. So here we have the CTs and PTs. For example, you can test them with test setup modifications, or you would have incomplete results if you don't do modifications. And we're going to see about that. Circuit breaker timing and travel, you can still use the conventional method, but again, you need to modify your setup. You need to remove the links, or you may not get all of the results that you want because everything is grounded. So you could still get travel, you could still get the coil current and all of that, not related to the actual main contact timing. And then there's a conventional test setup, the one with the check mark, that you can do the test without any problem and still get the results easily without any modifications. And then the diamond indication, it's the conventional test, but sometimes you need some accessories to be able to do the test. So it's a little bit of a summary here, what you can do, and probably it's not thorough, and there are a couple of things that could be added, but it's something that gives you an idea of what can you do with the in the GIS. There are standards in the IEEE family. The C37122 family is the kind of the document that contains most of the GIS standards. And in the IEC world, 62271 is the family that talks about switchgear, and some specific documents that, like the 203, is the one that talks about the GIS, or in general switchgear above 52 kV, and they talk about the GIS there. So just some reference there if you want to look more into GIS. Next would be dual ground and contact resistance. So this is a short section before handing it out to Daniel. And in this section, we are going to, well, basically you can do the contact resistance, yes, through the conventional method, but to be able to do these, you need to remove the grounding link. As the diagram here shows, we have removed, or we have represented removing the link here. So now you have path through the breaker and through the tank, and basically these are going to be your two terminals. It's not safe, and you have to do extra work. So that's one of the things that we already saw. You're going to have these induced voltages there, and it's going to be dangerous. But if you want to do it, or if you can do it, and it's something that you already know, or are clearing out and making everything work to be able to test like these, or during commissioning, well, you can still do it, and you're going to have your result. If you do the conventional method without removing the link, you have to be mindful that now your current is going to be circulating through a parallel, through two parallel paths. And usually the grounding path is a very low resistance path. So if your intention is to measure the resistance of the circuit that is represented here in red, the internal circuit, then your current, your actual measurement is going to be much lower than what you are expecting, because you have there the parallel path of the ground. So probably not the best thing. And actually, as I was mentioned before, the the resistance of the entire path is very important because you have the different modules, the different sections. So you can do dual ground. That means that you can run the test with both sides of the GIS grounded and without doing any modification. You just need the typical uh, digital low resistance ohm meter and add one accessory to measure the escape current through the grounding path. So in this case, you can see we have exactly the same connections as before without removing the link, and we have a CT that is measuring that escape current. And whenever the instrument does the calculation of the resistance, because it knows what current it is applying and what current is escaping to ground, now it can use the actual current that is circulating through the breaker to do the calculation. And again, this is especially crucial on GIS because the ground resistance loop is too low. You doing this, you have a method that is safe, simple, and fast to do the test. A couple of recommendations when doing the test. IEEE requires 100 amps to run the test. IEC requires 50 amps. So if you're doing whatever method you're using, you always think about the current that you're going to be injecting. And if you are doing a dual ground or in any case, be always aware that because the low impedance to ground, you may need an instrument that can inject more than the standard is requiring, because most of the current is going to circulate through ground. And in that case, you are not going to be running the test as per the standard. So typical instrument to use in this type of setup is an instrument that uses or can do up to 600 amps. If you are using an instrument also that can do that type of current, also be aware that you can adjust the ramp of the increase, the initial increase of the current. If you inject 600 amps or whatever 100 amps you are using to run the test, and it's a very fast increase, and remember that you are circulating current through the CTs. And if those CTs are active or connected to a relay and the relay is active, you're going to trip the breaker. So yes, you can close it and test again, but having a trip in the system is not good. And you may also trip other protections that are kind of looking into that trip, like a breaker failure or something like that, or a differential relay, sorry. So that's another important thing. And then you need to demagnetize the CTs after testing, because that current circulating through the CTs, primary side of the CTs, is going to magnetize the CTs. So you don't want to have that condition. So that's another thing to consider. And again, mind the protection scheme to avoid any trips. So with this, I finished my section. We are going to move on to the circuit breaker timing. Daniel is going to take over the presentation, and while he does that, basically what we need to be mindful of is that we always need to understand the GIS and know that there are some tests that we can do easily. Others we need to understand better the GIS to be able to run the test. With this, I think Daniel is already under control of the presentation. So Daniel, go ahead.
Yes, thank you, Volney, and hello to our audience. Thank you for joining us today. So yes, let's move on to circuit breaker timing. Obviously, right, the circuit breaker is a very, very important part of our protection scheme. So we want to make sure it's in good working condition, and we're going to discuss timing measurements. As Volney pointed out, right, if we look at the traditional or conventional method to test, that entails the removal of those groundings, right? As that's the only access that we have to be able to connect to the system, the contact system of the circuit breaker. right? So we have to remove the shunt, right? So once that shunt is removed, then the circuit breaker is in open position. The housing of the insulated earth switch ends up in a floating state, and that will be exposed to capacitive coupling from nearby lipers, right? When you're doing maintenance testing, of course, if you are performing commissioning tests, well, you're free to use this method, right? Again, you remove the shunt and then you connect the circuit breaker analyzer, you test using the traditional methods. And again, what happens if you don't want to go into that route, right? Of remove. Sometimes even the process of removing those links it's a task in itself is not as easy sometimes. We have alternatives. Only briefly mentioned, right, when he had the overall table on testing. I'm sure you heard or you have heard of DRM. In this specific application, DRM is possible with the removal of the link, right? In other words, a single ground. Sometimes, DRM is marketed as a dual ground method, but it's not the most accurate way to run this test. And again, in the case of the GIS, not really possible with dual ground because of those parallel paths. Typically, that earth circuit, grounding circuit in the GIS has a very low resistance, so that makes that DRM method not feasible for this application. So we go into a different technology, right? DCM, the dynamic capacitance measurement, where we use the same instrumentation, the same type of circuit breaker analyzer, plus a couple of accessories, the DCM box, right? Again, the dynamic capacitance measurement, plus some ferrites. This is a fast and most importantly, a safe method to test timing on my circuit breaker. So what this method will use is a high frequency signal, right? That's why we need that extra box, the DCM box. And in general, right, we're not going to go into the specifics, but in general, the method will use, right, the detection of capacitive current to determine the state of the breaker when the breaker is closed and when the breaker is open. As you can see in the diagram, the ground link is not removed, right? But I do have an extra accessory there, right? That green box that I'm showing in the diagram. So those are the ferrites. When we connect, right, the DCM without the ferrite, right, again, we have those parallel paths, and if we use the method or we tune the system, right, there's a tuning process that it takes just a few seconds. If you tune it without the ferrite, well, our signal will travel primarily through the ground path, right, which is, again, not the ideal scenario. We won't be able to test. So that's why we install those ferrites. So they will act as a filter. They will block the high frequency signal we are using for the test, and it will force that signal to travel across our circuit breaker path, which of course is the element that we want to test. That obviously not only gives us the advantage of being able to time our circuit breaker, but to also leave additional grounding points connected, right? So again, that's what I'm saying, that it's not only safer but also a fast method, right? We no need to uninstall those extra or additional grounding points. All you have to do, if you have them, is install the ferrites on those pads as well. So again, so we want to force our signal to travel through the circuit breaker. So how does that look in real life? As Bonnie mentioned, right, several times, and I'm going to keep saying it, all of these type of installations, the way you perform the test, a lot of times will depend on the type of GIS system that you have. Here I'm showing you an example where we have a single copper bar, right, rounding our three faces. So again, we're not going to uninstall it, but rather install these ferrites in between our faces and in between our ground. And in the third picture, you see we connect, even the connections are easy. This is our only point of connection plus grounding our analyzer. So that's all we need to perform timing on this case. We wanted to show you an example of results, right? On this particular case, where we're testing a Siemens breaker on a GIS installation, we were able to perform conventional timing, and we wanted to perform conventional timing because we wanted to compare, right? So people might wonder, okay, I have the DCM, and you were pointing out, okay, DRM is probably not the most accurate method. So how accurate is the DCM technology when we use it to time our circuit breakers? So again, showing here the results for conventional timing when we remove those grounding links. And now pay attention to the graph. It's pretty much the same if we look at the DCM timing, right? You can see the time in this case, the close operation, I mean, pretty much the same values, right? Looking at another example, in this case, a Hyundai installation, 123 kV. Same thing, we were able to perform, but I'm only showing the DCM results for the close operation here, the open operation. And notice one thing, our results are also showing motion, right? A very important measurement on all circuit breakers, right? And the GIS breakers are no exception. So you want to perform motion, and again, the ability to connect or install a transducer will depend on your installation. This is the same installation I'll show you the results in the previous slide, that Hyundai installation, right? In this case, we as you can see, mounted the transducer, a rotary type in this case, to the GIS mechanism with a magnet. In other types of installation, actually the transducer will be permanently installed. All you have to do is remove, the housing or an access door, and you just connect your analyzer directly to, again, a permanently installed transducer. So very important to perform motion as well. So now let's move on to our instrument transforms, right? As Bonnie already pointed out as well, pretty much traditional CTs and VTS, the installation is different. Yes, so we face those challenges that Bonnie discussed initially, right? Is configuration dependent. Of course, our only access to the primary terminals of these two elements as well is our grounding points or earth links. If we are testing on a energized environment, yes, we have isolated the section for the CT, the VT that I'm testing, but I'm exposed to capacitive coupling. If I remove those links, Bonnie also discussed the interlocks, right? When we're doing commissioning, you might be able to defeat some of those interlocks. When we're doing maintenance testing, we want to be very mindful, very careful, analyze the whole situation and see if we can actually do that, or we cannot perform it if an interlock is preventing us to do so, right? We also want to be mindful if those CTs, VTs are connected to a differential, right, to a protection scheme. Of course, don't want to make any nuisance stripping of those protection schemes. And again, the access to grounding links is paramount for us to be able to perform the tests. So I'm going to use the same GIS installation that I'm going to use initially, right, to discuss the test. But once again, this will depend on the particular installation you're testing. If we look this time at the CT here, right, in this single line diagram here. So what are my closest access point that I have through the earthing switch? So it's going to be this one on the right and this one to the left, right? So Of course, I want to make sure those two are grounded before I close the breaker. And let's start with insulation resistance. Only secondary to ground, and I'll explain why only secondary to ground in a minute. But again, you have this earth link axis, which I'm showing a little bit bigger here. And as I showed in the picture, right, for the DCM connections, you have that bar. You have to remove that bar, right? So you remove the earth link so you have access to each one of the faces that you're testing, right? And then our connections for secondary, right, where the access to the secondary is going to be done through the local control center. So that's what I have. In this case, a unit like the MRCT, or if you have an insulation resistance tester, all you have to do is access to your secondary winding, again, to perform insulation resistance secondary to ground. Why are we not doing primary to ground or primary to secondary? That will depend on the installation. For CTs, you can have both internal or external type. External type means that the CT is actually not inside the gas insulated chamber. Right? As you can see here in the diagram, it's external. So pretty much like a typical CT on a breaker or a transformer, it's outside the enclosure. So later in the presentation, Charles is going to cover insulation and testing for the GIS, and if that is the case, I mean the insulation system is assessed as a whole. So that's why we only do secondary to ground resistance for the CT. Another test we can perform is secondary winding resistance. Again, we need access to the secondary connections through the LCC, as you can see in the slide. We'll inject a current on the secondary and measure the voltage drops. Again, a unit like the MRCT, you'll be able to test a multi-tap CT in just a matter of minutes. We're leaving our primary connection just for safety. As you can see here, our ground link is removed, but we are connecting our primary lead as well, as the unit will ground this H1 lead during the test. For CTs, we can perform saturation, right? Once again, the unit will use the secondary leads to both energize and measure to perform this test, and we leave our primary lead connected just for safety reasons. When we move on to TTR and polarity, you can see if I go back, my diagram has a lot more color, right? In this case, we do need to energize one side of the CT, in this case, the secondary, right? Really important, we want to step down the voltage, and we measure to our primary. But remember that our only access to the primary is the grounding link, right? So we're pretty much using the whole enclosure, right? The tank of the GIS as our primary to be able to measure that induced voltage. So you can be very mindful of this situation, analyze the circuit, analyze the whole situation, and determine that in fact you can perform this test without compromising safety, right? Let's move on to VTs. Once again, using the same example. I use the same because if we look back at the CT, right, we had almost immediate access. Those earth switch, the earth links were pretty close to the CT, but as you can see, we cannot use this to test our VT in this part of the circuit. We'll have to go all the way back to this one, the same one that we were using for the current transformer. So we'll use this one and this one as our access points to the primary of that VT. So what measurements can I perform? Same thing, secondary to ground insulation resistance. You only connect to the secondary side with in this case, the primary lead set from the MRCT. You use that lead set to both energize and measure your leakage current in this case. For secondary winding resistance, right, we switch on the instrument side to our X lead set, right, our secondary lead set from the MRCT, and we can energize and measure with the same lead set on this case for secondary winding resistance. And the last one is also ratio and polarity. Of course, we need to remove the earth link because just as with the CT, we are using the primary, or the earth connections to access the primary of our BT. And again, on this case, we painted also the enclosure red because that's part of our primary circuit. So really important that you, again, analyze the circuit, make sure that it's a feasible situation for you to perform this test. After you finish, of course, make sure you ground the whole section back before opening the circuit breaker. And in the case of the CT, Paul mentioned when he discussed contact resistance, right? If you're doing winding resistance, that is a DC-based test for the CT. So remember to demagnetize the core. And with that, I will transfer the control to my colleague Charles for him to cover insulation testing.
Oh,
All righty. Should be up there. All right,
yep, we are good to go.
All right, thank you. All right, well, thanks, Volney, and thank you, Daniel, for covering the electrical testing on GIS. We will go ahead and now transition on to the insulation testing, in which we will focus mostly on partial discharge testing. So as both Volney and Daniel have mentioned, you have your simplified cross section of GIS here, where you have your enclosure, which is at your ground potential. And then you have your insulating material or your dielectric, which would be your SF6 gas. And then in the middle, you have your high voltage conductor. And, you know, it's important to remember this because these are designed that way for a reason. For instance, they're designed to have homogeneous electrical field. So that way you can see that your high voltage conductor has the same electrical field throughout the enclosure of the GIS, which is important. Also, the electrical field strength is below that of the critical field strength, which of course we know we would want. If it was exceeding the critical field strength, then we would have, you have multiple problems upon the stress upon your dielectric material. Now, there is some cases in which you may have a defect. For instance, here you have a defect on your high voltage conductor, and what this does is this causes a field gradient, and the field gradient is seen here by the electrical field focusing somewhat on this defect. And what this causes is you see a congregation or an isolation of the electrical field due to the field gradient of that defect. And what this causes is the electrical field strength to be above the critical strength, where we have kind of the even homogeneous field down here. Because of the defect, we now have this isolation or congregation of electrical field here. And because of this can cause partial discharge inception. That's especially kind of prominent in the SF6 because it's electronegative gas, but we'll focus on that on another slide. Now, partial discharge emits energy in several different ways. One is electromagnetic emissions. It can be in the form of radio waves, light, heat, and transients themselves. So, and those are ways that we can decouple the partial discharge activity from the GIS. Another is acoustic emissions. These can be both in the audible or ultrasonic ranges and are typically used for location of the partial discharge activity. The third that's listed here is chemical byproducts, and it's important to mention this because we'll focus on why chemical byproducts may not be the best way to determine if you have partial discharge activity, but it's good to know that partial discharge emits chemical byproducts because it emits ozone, and ozone is particularly corrosive, and within the enclosed environment of a GIS, which is majority metallic, of course, that ozone is extremely corrosive and can cause extensive damage. And all of those, as you can see, can lead to deterioration, which is not something that we want. But you can have partial discharge signals that indicate your imperfection, and what you can do is you can identify that partial discharge. And this identification or detection gives you the detection of the risks and hazards once you identify it. Then from there, you can localize it, which gives you the ability to schedule maintenance works to try to rectify those issues. And even more so, you can actually classify the partial discharge activity that's taking place, which gives you the ability to rectify or fix that issue once you identify, localize, and then classify it. And that overall gives you the increased reliability within your GIS system. Here we've talked about, or we previously talked about the several different emissions that partial discharge activity emits. And here is kind of a graphical, or I guess an illustration of that, where you have partial discharge within your installation. And you can see that the physical effects give off optical, mechanical, electrical, and chemical emissions that we can detect. For GIS in particular, we're looking more at the EIC 6270 method and the UHF method. And we'll go into detail because the EIC 6270 is the conventional method, which is really just used for the sensitivity check. But again, we'll go into this in greater detail. So talking about the conventional method, as I said, the conventional method is performed in accordance to the IEC 6270 standard, which is basically the Bible, if you will, of partial discharge testing. And in this case, you use a coupling capacitor to decouple the partial discharge activity while inducing partial discharge with an external high voltage source. So this is an offline test. Now, of course, we can see the issues with doing this on site. One, the GIS would be difficult to take out of service and hook this coupling capacitor up to, which is why you can see down here it can't be applied in service. But also we have limited sensitivity on site, where the customer expectation is going to be somewhere in the realm of 5 picocoulomb, and the common background noise is going to be anywhere from 10 to 100 picocoulomb. Also, with the conventional method, you kind of are lagging in the fault location ability. Over to the right here, we have the chemical detection, which again, you have the slow process. And then, of course, due to the insulating barriers within the GIS, this limits the detection ability whenever trying to test by the chemical emissions. Also, you have optical, but certain defects can't be detected. For example, voids within your maybe epoxy insulation. So these are just kind of highlighting some of the detection methods. Talking about partial discharge itself within SF6, which is our insulating material on our gas insulated switchgear, SF6 is an electronegative gas, and electronegative means that it has a higher probability of accepting electrons. And for partial discharge to take place, there must be two conditions. One is that the electric field must exceed the critical electric field, which we kind of saw in the earlier illustration. And then the second is the availability of an electron. So because of the extra availability of the electron, or the extra statistical probability of SF6 accepting an electron, the rise time of the discharge is actually 100 picoseconds, which translates to a frequency spectrum of several gigahertz. So very high frequency discharge. Now, when we look at partial discharge with the nitrogen, which is more or less the air conditions, since air is 98% nitrogen, we can see that the difference in the rise time, we can see the rise time is only 1 nanosecond, which only translates to a few hundred megahertz. So the partial discharge, or the spectrum of the PD pattern within GIS is completely different than that of an air insulated medium. So PD activity emits transient electromagnetic waves. We saw that earlier. Now, the good thing about a GIS being enclosed is the fact that it actually acts as a waveguide. So electromagnetic waves travel through the SF6 like radio waves through air. Or if you imagine yelling into a hallway rather than an open room, you know that the person at the end of the hallway would hear you better than the person in the open room. So this enclosed environment actually acts as a waveguide. Also, this is a broadband signal, and this is because of the complex signal propagation. So even though the GIS acts as a waveguide, that doesn't necessarily mean that the wave or the signals travel through without any issues. And we'll go into those on the next slide. So what I meant by that was, as both Volney and Daniel have touched on, the GIS has a very complex geometry, and this leads to reflection and signal attenuation, especially at these high frequencies. Also, the impedance of the waveguide is a function of the different diameters of the changing travel length within the GIS. Also, at these high frequencies, you even have dispersion through the roughness of the surface roughness of the GIS itself. So that can influence the wave of propagation within the GIS. Again, these effects are highly frequency dependent, and because these are very high frequencies, you know, they handle these, or they affect these frequencies or signals very, very much. And as an example, you have a PD pulse here. So you can see your high rise time and settling time, and this doesn't look too bad, but this is at the point of partial discharge. If you were to look at the point of the terminals in which you actually get the partial discharge decoupled, you can see that this actually turns into a pulse package. And the original pulse becomes this oscillated pulse package. And again, this is due to the reflections, refractions, and attenuation. So you can see the difficulty of translating one to the other. So you can see the effect of these high frequency attenuations and reflections to the partial discharge signal. So again, the partial discharge is a broadband measurement, which results in a wideband measurement to require, or achieve good sensitivity throughout the entire GIS. And instead of using a coupling capacitor, we actually use multiple UHF sensors to measure the partial discharge activity. And we'll go into that in greater detail. But these UHF sensors act as an antenna and convert the electromagnetic wave to a voltage that you can measure. And that's due to the fact that, again, we can't really once it's in service, we can't really access the primary, we can't really take this offline. So we use these unconventional methods, such as the UHF method, to measure and decouple the partial discharge activity. And talking about those, here we have a couple of examples of UHF sensors, where first we have an example of the external flange sensor. Now, the external flange sensor is really good for retrofitting pre-existing GIS without opening it at all. So on GIS, you typically, on these connections here, have epoxy insulators. So you have your gas insulated line, and your flange, but in the center of the flange, you typically have this epoxy strip. And we can't decouple the partial discharge activity through the metallic surface, because obviously that acts as our waveguide. So instead, we focus on these epoxy insulators here, where we can add these external flange sensors, as seen here and here. to actually decouple the partial discharge activity. Now, since they're on the outside of the GIS system, this does result in a lower sensitivity, but still allows for the versatility of installing these on pre-existing GIS systems. Now, another option would be window sensors. So if your GIS has windows that are greater than 60 millimeters in diameter, you can actually attach these window sensors as seen down here and seen in the illustration here where they're actually attached. And we'll talk about this frequency converter, but you actually attach the window sensor here, and again allows for retrofitting of pre-existing GIS without opening it at all. Again, since it's on the external of the GIS, it still has lower sensitivity, but still offers the ability to retrofit your GIS without opening it or taking it out of service. Finally, we do have the ability to use integrated or embedded UHF sensors, and you can see the large frequency range that we have here between 200 megahertz and 2 gigahertz, so giving us that wideband measurement. They also offer the best signal to noise ratio, as one would imagine, because they're internal to the GIS. So as the GIS acts as a waveguide, that signal can be decoupled directly from inside. And these can be installed during the manufacturing process and are often provided by the GIS manufacturer. You can also use the implementation of the input frequency protection in close cooperation with the GIS for integrated embedded sensors. Now that we went over the sensors, I kind of want to just go over a couple of different diagrams for measurement. And this is an example of one using the window sensors. So again, we have our window sensors on our GIS. As seen down here, we saw this previous image. Here's one here. And again, we have our frequency converter unit. That's the FCU here, as seen here. And that converts that frequency down to a lower frequency to be accepted by our measurement system, which is the AIA compact here, used for unconventional measurements. You can see it's set to the UHF mode. So it has automatic detection of sensors, and again, we can detect partial discharge using these window sensors and our measurement system here. Another example would be using the external flange sensors that we had previously discussed, where you can see an external flange sensor here on the flange itself with epoxy, but you may not always have the ability to have that. For instance, if we look at the image here, this is a metallic surface. This is not the epoxy surface, but several of these have these nameplate covers, and often if you remove this nameplate cover, you can see the filling of epoxy within underneath it. So if you were to simply to add your external or your sensor here, your external flange sensor here, then you can decouple through that epoxy there. So same idea, where you have your frequency converter unit, again, out to your AIA compact, which is your measurement system, in your UHF mode. So again, showing an example of two different measurement circuits, depending on whether or not you have the availability of windows in your GIS, or maybe you have flanges in which you can use these external flange sensors. Now I just kind of want to show you an example of some measurements. These are provided by our fellows at Power Diagnostics, so fellow co-workers at Power Diagnostics in Germany. And here's an example of a moving particle, also often referred to as a hopping particle. And this is mostly caused by the GIS assembly, where you may have some shaven metallic particles that may have made their way into the GIS. And these can be lifted by the electrostatic forces and can actually jump towards the conductor, hence the word moving or hopping particle. And breakdown can occur whenever those particles get close to the HV conductor, the high voltage conductor, or through contact of the insulators. And these are known by these predominant kind of humps here, where you can see kind of a lower magnitude down here and a higher magnitude here, right on the peak of the applied voltage. So again, just kind of an example of a common defect within GIS. And this is the phase resolved partial discharge pattern that would come of it. Another example would be a protrusion. And the protrusion is mostly likely due to scratches in your GIS. These often have low partial discharge level, and it's kind of relative to the sharpness of the tip. The sharper the tip, the higher the voltage gradient at that tip, which makes it easier to detect. Now, these tips can change over time, which can change the level of partial discharge as the degradation increases. And they have significant polarity effect, and this allows you to actually the position in phase allows you to indicate whether or not the protrusion is on the ground or on the conductor. So that polarity effect actually helps you out in trying to identify what kind of defect, and not only what kind, but where is it. And the third and final example I have here is a void discharge, in which the partial discharge inception requires your starting electron. And these voids are difficult to detect during the acceptance testing, now where GIS manufacturers have implemented PD testing under the X-ray to detect voids. So you have to actually use an X-ray to excite them, create that initial starting electron that we had previously discussed, which would then start the partial discharge pattern. At the top here, we can see that we have one void on each side of the phase, and this is of longer duration, and which is why we have this more counts within this. So the gray dots are the actual counts of discharge, where the red and orange here is higher counts, so higher repetition of discharge. Now down bottom though, we can see this is more like fresh voids within epoxy insulator, and we can actually count 6 of them. So we can count 1, 2, 3, 4, 5, and then 6. So you can actually see you don't have just one single void within this one, but actually multiple voids. So it allows, again, for not only the detection of the type of defect, but even the number of them at this case. Now, partial discharges, we've talked about, we've used the conventional and unconventional method. Now, you only use the conventional method of testing during the manufacturing process for what's called the sensitivity verification, which is a 2-step procedure for acceptance criteria. And the UHF method cannot be calibrated, and we'll look at that on the next slide. So due to that, you need this sensitivity procedure or sensitivity verification as described in the following C-grade documents listed below here. So within the C-grade document, you can see that there's a quote here that for the unconventional UHF method, a calibration to apparent charge, which is measured in picocoulombs, is not possible. Therefore, this measurement is actually taken in decibel microvolt or decibel milliwatt. And there's a conversion factor here if you're using a 50 ohm system, such as a coaxial system. And you can see that your partial discharge defect, again, sends out the electromagnetic wave signals, and you can actually decouple them using the UHF sensors, and you can actually see the effect of the attenuation and other high frequency signal effects as the signal starts to attenuate and lower due to dispersion and reflections and so on. Now, when we talk about the sensitivity verification, the first step is a laboratory test. And this is where you have your parallel measurements of your conventional method and the unconventional method that we had previously discussed. And in this situation, you have a real PD source as seen here in A at C1. So here you have a real PD source of 5 picocoulomb. And you know that by verifying it through the conventional IEC 6270 method. We're using a coupling capacitor and high voltage, as you can see here, to induce the partial discharge. And you know now that it's 5 picocoulombs by measuring it through the conventional method. Now, you also take the measurement of that 5 picocoulomb translated to a voltage, which would be signal A as seen here through your UHF sensor. Next, you have a pulse generator in which you input a pulse, a variable amplitude, and you tried to match that signal A that you had taken previously with that known 5 picocoulomb defect, so to where your signal A should match your signal B. And now you know the pulse generation that was injected in to cause that. So this allows you to determine what type of impulse generates the same amplitude and frequency spectrum as the real PD source that we found in this A here. And the result, it's important to note that the results are valid for this type of GIS, the sensors used, and that impulse generator only. Once you change some of these variables, that's no longer the case. Same with a calibration. You have to calibrate with that circuit in place. So this can affect your sensitivity check or your sensitivity verification. Here we have kind of just an example where we have the artificial pulse magnitude of both 5 volts and 10 volts for the bouncing particle sensitivity check, in which we're using the phase resolved partial discharge pattern. So the idea is to match this injected pulse to the peak of the 5 picocoulombs that we have. So you can see where the 5 volts is and the 10 volts is in relation to the peak. Again, captured in your phase resolved partial discharge pattern. So again, I just wanted to show an example of that step there. Next step is our step 2, which is our on-site step. So the idea is to inject the voltage that you found per step 1 into a UHF sensor, and then measure the surrounding sensors. So we can see here, we've injected our voltage that we found, and we can see the UHF signals or the PD signals that are found at the other UHF sensors. And as one would imagine, the further away or the further the more complex the signal propagation is, the lower our signal is. But all that's necessary is that the signal is above our noise floor. And you must check every measurement pass. So as we've done here, we've measured here, 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 and here with our UHF sensors. And we've looked and we can tell that through this, that all of them pass. All of them are above our noise floor. So we're able to see the PD signal here, here, and obviously greater here, and even greater as the closest we get to where we injected our pulse generator. Now, as we mentioned, for the acceptance criteria, it's necessary that each sensor picks up the signal at least once, and also that that one measurement be through each part of the GIS. So that way you can ensure that you're able to detect all partial discharge impulses of 5 picocoulomb or above at all areas of your GIS. So again, this gives you kind of the sensitivity verification, or the quote unquote calibration of your GIS system for partial discharge. Now, in conclusion, we've talked about electrical testing and insulation testing, where GIS have reduced electrical testing and are known as quote unquote maintenance free. But as Volney and Daniel have touched upon, we know that it does require some maintenance. And when testing, or when needed, testing requires the preparation and knowledge of your GIS, as well as knowledge of alternative techniques that were discussed in this presentation. And some tests may not be possible to perform. So you have to be aware of that. And again, knowing some of these alternative techniques may help you in that situation. And safety requires closer attention to knowing what's taking place. And finally, partial discharge occurs, as we talked about, due to imperfection and defects that causes deterioration and emitting energy that we can measure. And the partial discharge within SF6 emits a UHF signal, or I guess I should say ultra high frequency signal, that's wave guided by the GIS, but it causes this complex propagation. And we saw the effects of attenuation, reflections, and dispersion when we tried to measure the signals further away from where we injected. And that as we saw, the UHF partial discharge pulse package can be picked up by various different sensors and antennas. So that could be our window sensor, our external flange sensor, or even the internal embedded sensors. And the UHF method cannot be calibrated, so you cannot measure in picocoulomb, but instead you use the acceptance testing of the by use of the sensitivity verification. So that way you can verify, you can measure defects of 5 picocoulomb or greater. And finally, SF6 gas requires a separate analysis. So just kind of wanted to cover that this is more over the partial discharge testing. So to analyze the SF6 by itself, that would require a separate analysis. Alrighty, and I think that finishes it up for today.
All right, good deal. So at this time, the presentation portion of our webinar has officially concluded. We'll now take some time to answer as many of your questions as possible. If you have any questions, please submit them now into the Q&A box on the right side of your screen. For those of you that are leaving, when you close the webinar window, a survey should pop up on your screen. We would greatly appreciate it if you could take a couple of minutes to provide your feedback so we can continue to improve upon our future webinars. On the survey, there's also a field where you can request a quote or a demo of any Megger products. As a reminder, a copy of the presentation, certificate of attendance, and a link to the video recording of the webinar will be emailed to everyone in about 2 business days. You can also view video recordings of previous webinars as well as register for our upcoming webinars on our website at us.megger.com/webinars and register for our You Ask, We Answer, a panel discussion on cable diagnostics. All right, let's get into your questions. Our first one I'll direct towards Daniel. Daniel, what is the recommended method for demagnetizing CTs?
Thank you, Michael. Well, the preferred method is the AC method, right? A unit like the MRCT can go to 2000 volts AC. So then it would slowly ramp it down to demagnetize the core. But it is also capable of using a DC method, right? Where it will just start from a value typically the same that it was used for the testing, and then slowly go down, reversing polarity, doing several different passes, again, reducing the amplitude and changing the polarity. But the preferred method is using AC, which the MRCT can do.
All right. Next is over to Volney. Volney, the ferrites are inductors that are low impedance at 50 hertz or 60 hertz and high impedance at high frequency?
Pretty much, but actually the ferrites are not inductors, but they are ceramic. They are a ceramic material that act as a magnet. So you can see it as a core of a transformer if you want to. So basically, at high impedances, they will act as a at high frequencies, they will act as a high impedance. And you can see the use of ferrites very commonly in cables that we use daily, like the cables that connect your monitor to your computer, or the power adapter that you have for your laptop. They will have a little cylinder next to the connector. So those are ferrites, and they are there to filter signals or filter noise coming from whatever you are connected to go into your computer. So they are effectively a high impedance at high frequencies, but they are more like a magnet or a ceramic material instead of an inductor.
Thank you, Volney. Next is over to Charles. Charles, in regards to PD testing on GIS, is online more accurate than manual testing?
So I assume that this is the either online monitoring, well, online measurements is really all you can do on GIS. So there is no offline measurements on GIS. The only offline measurement that we spoke of was during the sensitivity check that we mentioned, which is in the manufacturing or acceptance process. So I'll go ahead and answer that as far as online periodic versus online monitoring, I suppose, because there is no offline testing of GIS. But I wouldn't say one's more accurate than the other. The only thing that online monitoring would give you is the ability to I guess, monitor continuously the partial discharge activity and set thresholds and alarms and such, whereas offline would allow you, or I guess not offline, but periodic online would allow for the ability to come in and do the testing periodically, but there's not really one more accurate than the other at that point. They're both online testing. The only difference is one would be periodic, one would be continuous. So again, I assume the manual testing meant offline. I'm not exactly sure, but there is the only offline testing you do on GIS is again during that sensitivity verification.
All right, thank you, Charles. Next is over to Daniel. Does the MRCT test set demagnetize the CTs on its own?
Well, yes, the MRCT, when you look at the software, there is a feature called run all tests, where you just click and say, okay, I want to do everything possible on a CT, and certainly after the DC-based tests, the unit will automatically go to a demagnetization routine before performing ratio saturation of the AC-based measurements. But I would say, we are discussing GIS testing today, and as you saw during the presentation, you really have to analyze your connections, make sure that everything is safe and that you can perform each and every measurement. So typically for GIS, say you seldomly use the run all. So yes, you still have the capability to demagnetize, but you have to yourself click the button to demagnetize and do it individually. But yes, the unit does have the capability.
All right, thanks, Daniel. Next is over to Charles. Is the propagation of PD signal inside GIS happening through the conductor or gas? And what happened if there's an interruption by CB or disconnector between PD source and UHF sensor?
That's actually a good question. The actual propagation is happening through the SF6 gas in combination with the enclosure itself, acting as a waveguide. And the issue, if you do have an interruption by circuit breaker or disconnector between your partial discharge source and UHF sensor, typically you're using multiple UHF sensors, as we saw in different areas of your GIS. Now, you may have an interruption on one sensor, but you should be able to pick something up on another sensor, which should give you a relative idea that the partial discharge is over in that area. And the beauty of these UHF sensors is you have multiple, whether they be internal or embedded, where you can move to another sensor within the GIS, or if you have the external flange sensor or window sensor, you can move to another area in which you have the ability to apply that UHF sensor where you are getting a signal, and you can basically kind of track down that partial discharge source. Another method that wasn't really highlighted here is the acoustic method that would also help you in localizing partial discharge within your GIS. This was more on the measurement of the partial discharge itself, but you can also use acoustic methods to help localize the issue, but still using the UHF sensors, you can still have the ability to move those sensors, since they're either external or you have multiple embedded sensors. So as long as you're picking up a PD signal on one of your sensors, you would have an idea that the partial discharge source is in that section of your GIS.
Great, thanks, Charles. Next is over to Volney. You mentioned first trip as a test for the circuit breaker. What is first trip test, and can I measure breaker timing with this test?
Okay, yeah, we didn't cover that technique in this presentation. We have other presentations that talk about the first trip, but in summary, first trip is a test that measures the specifically the current of the tripping coil after the breaker has been in closed position for a long time. So that is a technique that is used to get information about the mechanical condition and the coil condition, the mechanical condition of the breaker and the condition of the coil, and in this test, typically in any type of breaker that you run it, you are mainly measuring just the coil current and the voltage that is applied to that coil. In combination with these tests, you can also use some CTs to measure the current on the load side of the breaker. You measure that current at the CTs of the system. So the main CTs on the primary side of the load of the breaker, you connect your ammeters or your little CTs to measure the secondary current. And when the breaker is tripped, those CTs are going to detect, or you're going to see that the current disappears. So that is the moment that the breaker is has opened. So it's an indirect method to measure the timing of a breaker. It doesn't give you the exact timing of the contact, but it's very close, and it's used commonly as a technique to measure the operating time of the contacts, or to have a close measurement or idea of what is the timing of the breaker. And it definitely can be used on GIS as well. It's used for any type of breaker, high voltage breaker, and definitely can be used for GIS.
Thanks, Volney. Charles, if there's no metallic window on GIS flange to be removed for installation of the external UHF sensor, can it be installed other places?
Sorry about that, Michael. It helps if I take myself off mute. No, thanks for that question. So you can do either or. So you can install window sensors on existing windows, or you can do flange sensors on flanges where you have epoxy as the insulating material there, or as we saw, maybe even you have the nameplate there. So these can be installed other places for sure, but unfortunately, if you're using these external UHF sensors, be it the flange sensor or the window sensor, obviously the window sensor is going to have to be attached to a window, and the flange sensor being the same. It's going to have to be on a flange, and likely you should have a flange that either is made up of epoxy in the middle, as we saw, or has, even if it's metallic, should have that nameplate section that's typically filled in with the epoxy, and which these don't really require you to measure anywhere particular, which is kind of piggybacking off of the other question of the interruption by circuit breaker or disconnector, where you have the ability and the freeness of moving these sensors, as these are online measurements. I mean, the system is already online. All you have to do is take your sensor and move it to a window or a flange, and pick up PD activity. And if you don't, then you're always free to move to another window or flange. And typically, as we saw, you have multiple sensors, which is the point of this, where you can pick up a signal and then kind of migrate more towards that area and try to identify where that defect may be within your GIS system. So definitely these can be installed in other places, though these places are limited by the application of the sensor itself.
Hey, Charles. Daniel, if I have multiple CTs on the same phase, should I ground the secondaries of the ones not under test?
Thanks, Michael. Certainly, yes, primarily for safety. And it can also affect certain measurements like ratio. Short-circuiting those secondaries not under test, you can have a reflection on that CT that you're testing. So yes, you want to always short-circuit those secondaries not under test, primarily for safety, and they can also affect certain measurements.
Great, thanks, Daniel. Next over to Charles. Charles, you mentioned other types of unconventional measurements that can be performed. What would you recommend aside from UHF measurements?
Sure, I unmuted myself this time, so I got you. So this kind of, I touched on this previously with the question of the interruption by circuit breaker or disconnector. I would recommend acoustic measurements. I mean, if you have a UHF measurement and you have you picked up a signal and you know you have partial discharge activity, you can then at that point transition to acoustic measurements, which allows you to localize that defect again. So, and that can be used through, again, as we see on kind of the slide that's left up here, that AIA compact, you can use both UHF and acoustic sensors. So depending on the number of measurement channels you have, maybe you have both of them there. Or you have the UHF sensors, you identify you have partial discharge activity, and then you can switch to the acoustic sensors, which are something like piezoelectric sensors, because the partial discharge activity actually creates pressure waves that propagate through the GIS and can be decoupled through piezoelectric sensors and can help to identify where the partial discharge is taking place. And the beauty of the acoustic measurements is you can completely decouple these through the metallic surface of the GIS. So there are special sensors that are used to strap to the metallic surface of the GIS, which even gives you more freedom of placing your sensors along your GIS system, as you're not limited to the windows or the flanges when you're using the acoustic. Again, you can decouple these across the metallic surface. So, which is why they're particularly good at location.
All right, thanks, Charles. To Volney, can DCM be used for other circuit breaker applications?
Absolutely. One of the actually the very first method that, or the reason that DCM was developed was to test regular air insulated breakers, or breakers in air insulated substations with both sides grounded, and this was developed to improve the safety, to avoid removing the grounds once the breaker was grounded, for all of the maneuvers and the procedures to be able to test it. So that was the initial application of the DCM development from Megger 20 years ago. And well, as one of the benefits of using the DCM technology was kind of finding or using it for the application of GIS. So other breakers definitely can be tested, and there are some applications or breaker applications that definitely disconnecting them from ground, or they don't even have a way to disconnect, because there's a direct connection between equipment. So those conditions, those situations are very good applications for the DCM, not only GIS.
Thank you, Volney. Next to Daniel, can I measure closed open and open close open operations using DCM?
Thank you, Marco. Yes, you sure can. Svoni just explained DCM is a technology that can be used in a wide range of applications. And yes, as the name implies, right, it's a dynamic measurement. So just as with conventional timing, when you set up your circuit breaker analyzer, you define, okay, my length of measurement is 1 second or 100 milliseconds, whatever you decide for a particular operation, and that includes the combined operations like the close open and open close open. So yes, DCM will work for those as well. It will be just as accurate as with the single operation.
All right, thanks, Daniel. Volney, can DCM detect main contact bounces?
Yes, this is a very minor detail, while that you get when testing the timing of the main contacts of a breaker, but it's a very important detail to measure. You could have your the fixed contact could be loose, and it may cause disconnections, temporary disconnections of the main contact while the breaker is operating, and they are typical, or they are common to see those, but you don't want to have many of those bounces. And the conventional timing of a breaker detect these bounces, and DCM does as well. There might be other technologies that measure the timing of a breaker, like dynamic resistance measurement, but those are too fast, and the resistance changes, that the threshold is too small and too quick that the other technologies cannot detect it. So DCM it's a very good way to detect. And actually the presentation, or the slide where Daniel showed the results, actually has a couple of bounces, or at least a bounce in each of the phases. When you get the slides again, or after the presentation, you're going to see that in the slides.
All right, thanks a lot, Volney. It looks like that's all the time we have for our Q&A segment today. We apologize if we didn't get to your question live, but we will follow up with you offline in the following week. As a reminder, a copy of the presentation, certificate of attendance, and a link to the video recording of the webinar will be emailed to everyone in about 2 business days. I'd like to thank you all for attending. If you could, please remember to answer our survey. That survey will include a field for you to request a quote or a demo if you're interested. But once again, I'd like to thank you all for attending, and I hope you all have a great week.